I wanted to talk to you about the weekly schedule here. If you go to your planning your time on the website, you'll go to this crazy looking schedule, which has got more color on it than anything else. But actually, though, we are right in week 9. This week we have speaker Lydia Eckstein who's coming in, and she's going to be talking about how she uses work or how she uses data in her research in psychology. It's always fascinating to hear her speak. Um, and so we'll be having our lab, zooming into our lab on Friday, and she will be there. So please do not miss tomorrow's lab. I mean, please be there and come with your questions about her research, because I mean, this is it's a once in a semester opportunity to listen to Dr. Eckstein here talking about her research. I think it's actually quite interesting. Um, I don't want to give away too much of the details. I'll let her do that. But when last I heard her speak, I thought that it was probably one of the most. All my speakers are really interesting, but hers was very interesting for very different reasons. Um, it's just cool. It's just cool research. Anyway, I'll just put it. I'll leave it there, and so I'll let you come and listen tomorrow. But please do come with questions, ask questions. I mean, participate, be involved. The next thing I wanted to talk about was exam 2. Now, we the week after Dr. Eckstein's talk on week 10, this puts us about here on the 3rd, the 5th, and the 6th. That is well, it's a kind of a complicated week for several reasons here, because we have our election. And so here's the thinking behind this whole thing is I was thinking about canceling class on Tuesday so that you had time to go out and vote. I know that sounds like a ridiculous idea, but I'm sure you have enough time for, well, maybe not. If everyone's giving classes and everyone's doing things, maybe, for instance, you don't have time to get out there and vote. But also, though, it's just going to be a hectic day. If anyone is volunteering at the polls, for instance, voting, but if you're volunteering. And so I'm just going to go ahead and cancel class on that day just because it give you some time. But that means, though, that we couldn't have the exam on the Thursday because then we wouldn't have time to discuss it on Tuesday. Usually what I like to do is on Tuesday, remind everybody that the test is coming up on the Thursday so that you have this, you know that week, the next class, when your test is going to be. Now, the following week, we couldn't have the test because we have another speaker, Dr. Anyi Wu, which is another amazing speaker. I mean, he just really is an amazing. He's from our own economics department, and his research is fascinating also. And so there's going to be a lab that week, and so I don't usually like giving out labs and tests on the same week because it's a lot of it's a lot to process. So I was thinking that we'd have our exam on week 12 here, maybe on the 19th of November. That's like our last week before we get out of before we go to in person or before we go to online classes, because the in person classes end on the 27th, 26th perhaps of November. So that's coming up, and so I think I'll have the exam that last week there. And then, of course, after the classes on the 13th week, after the 14th week, then, for instance, you'll just have that time to work on your projects. And so I thought that actually it's not on the actual map here, it's on the calendar, but I thought we'd actually cover your projects maybe the same week that exam 2 is being given. So if on Tuesday at this time here, on the 12th week, I'll actually talk about what the projects are. So I wanted to give everyone here a heads up on what to expect, like what's coming through, just so that you know what this class is going to look like as we near the end of the semester. And so I don't want anyone to be surprised. I know that as data scientists, we do not like surprises. And that is absolutely true. We do not like surprises. And so I wanted you just to be aware of the upcoming exam and the cancellation of class on Tuesday next week. Today, the 29th of October, we are talking about modeling. Now, this is the basics of models. And so whenever you turn on to the news, in fact, just the other day, when was it? Just the other day, I turned on to the news and they're talking about the hurricane model that's happening down, the hurricane that's going on down in Louisiana and New Orleans down there. They're expecting, you know, well, it has been some bad weather, but they're expecting like, more types of bad weather. But they have all these so-called computer models that they're using to forecast the amount of rain, the amount of wind. How do they do that? How do they actually predict any of this stuff here? And mind you, this is actually almost magic. When you first hear the word of model, it's almost magic. Like, how can you use like just numbers to predict things? In other cases, we've been using models to predict COVID outbreaks. In fact, and you have data that helps you do this, but this is something I wanted to talk about, though. Just this isn't necessarily a model, a predictive model, but this is like a model where you can see the trends. I have this link here. Let me just go ahead and show you what it is. But it's an interesting thing for your own information, I would say. There's no test questions over this, but it's interesting for your own information. But this is essentially a type of a modeling system here, where you can see in terms of like COVID outbreaks and cases and how it's spreading, how the virus is spreading around. You can see, hopefully you can see what I'm pointing at here, these lines here. And so these lines could be considered types of models, where if you see in the United States, and this is really sad news, and I'm not just picking, I hate to talk about this actually. It's an emotional subject for very many people. But you can see that the model is predicting, just by the direction of these lines here, it's showing that the cases in the United States are increasing. And that's not good. So what we're seeing now is that although we don't have data right now from the what do you call it? We don't have data right now from the future. Nobody can have that data from the future. However, we do see that, I don't know if you can see one. I'm actually pointing at 1 day or 0 days ago at the very far right of the United States blue line. You can see that that line is beginning to point upwards. That is very bad news. That means that the cases are going up. Now, we can somehow model this in our head by saying that although the cases are going up, and we don't have information about what's going to happen tomorrow, according to this trajectory, as they call it, I can see that I can expect that tomorrow's numbers are going to be higher than today. In fact, I think that most of this data would suggest, like the European Union, for instance, that's even more steep. But that's all the countries combined together in Europe. And so that's why that European Union thing is going so high, because some countries are really having a bad time with this virus. And my heart goes out to them, as it does to the people in this country as well, who had so much, who've been sick and had to deal with this. But what I'm saying is these models that we're talking about here take this kind of idea that we can look at where the numbers have been and figure out where the numbers are going. And so that is really what they mean by models. And so these weather models that I mentioned earlier, again, it's like, where has the humidity been, and where has the temperature been, and where has what kind of rainfall have we had? We use that information to try and predict what we are going to have. Anyway, do spend some time looking at this model here, though. This is actually quite interesting. You can actually download the data from your. In fact, if you go down here, I think you can download the data from this plot, so that you can actually run your own analysis if you'd like, to see what kinds of cases are present in particular countries. One thing I will say, though, that you may be looking at this area here that says scale, log, and linear. Log kind of groups everything together. Linear has everything looking far apart. Now, the big difference is this, that when you look at log, it means that the small things become bigger, the small numbers become bigger, and the bigger numbers become smaller. But everybody, as long as everyone as long as all values, for instance, of y have been taken to have been logged, means you take the log of y, x, and then log of x for each of these points here. As long as you have a log, that means that everyone has been transformed. And so while the data that I'm looking at here isn't really actually landing at exactly where I see it, this does give me this ability to compare different countries here. because if I wanted to see how, for instance, let's see, who's at the bottom of the thing here, Portugal. Portugal 5 days ago, here I am, or Portugal one day ago. They seem to be doing very well here. I mean, as well as you can do for this pandemic. They're not the highest. They don't have the highest number of cases. In fact, in this thing over here, the European Union has the highest number of cases. And so, if I wanted to be able to see that difference, say who, just looking visually to see who has the highest cases. If I were looking at this as a linear graph, then looking at down here, it's kind of hard to tell who's on top because uh, everyone is like kind of muddled together. And that is because you're looking at everyone in kind of real time. You're looking at their own data. But one of the troubles is, though, that because the data up here is so great and the data down here is comparatively small to the data of the European Union, then it makes it very difficult to actually compare the data on some kind of what they'd call an even playing field, where you can compare across countries the same information. So if you take the log, then that means now all these countries, the numbers are not the same numbers you'd find in data, but rather they have been wrangled and transformed such that you can now compare the numbers across countries without worrying that, for instance, one number is so much smaller than the other that you can't see it on your plot. But now you can, because everybody is kind of clumps or groups together in more or less the same way. And so that's why when you look at these kinds of plots here, typically you'll have this scaling feature here where you can scale it by log or by linear. And if you look at by log, that's a tool you use to actually make direct comparisons across countries. Although the data has been changed to allow you to compare across countries. Or if you're looking at linear, that's how the data actually falls. But the thing is, though, that some data is so small that it just gets dwarfed by the Goliath of data that is the European Union here. Anyway, we have all this other stuff. You can even click on some other buttons they have mixed in here. You have the animation, so you can kind of go time, or you can look at your plot like as time is moving along here to get an idea about how things are moving. But remember, though, that we're talking about models. And so models tend to look at this kind of data and they say, aha, I see that these points are up. I'm going to predict statistically that the points will continue to go up because I have no reason to believe that they're going to go down. And that is one of the things. Um, I'm looking at the United States right now, and that dip that we're seeing right about here, that's in the spring or the late spring. That was in June, around June 1st, and then July 1st. And then July 1st, it began to really kind of take off. That was because in June, people were still kind of feeling optimistic that they were able to stay at home was doing something. But then in July, early July, there was like the 4th of July, there was Labor Day, and these other holidays where people went outside, and then that was where socially distancing and wearing masks wasn't happening, and we just had these outbreaks. It's interesting how the data moves around, though, and I think that when next year, hopefully when this pandemic is over and done with, we can go back and look at at some of these points, and when we actually go back to explain those points using literature and newspapers, I'm hoping that lessons can be learned, and that if any other pandemics happen, we will take ever. Anyway, I don't mean to rant, but that's why we look at this data, so that we don't forget, so that we learn something. Okay, so I'm going to go back now and get away from this for a moment here, but please do, go back to the site there and keep checking these. There's other plots there too, which I didn't talk about, but please go back though and keep checking this just for your own knowledge. This is another such plot here. There's a read that you can check out here. This is in fact something that this came out last semester, where they're talking about canceling events, if you cancel events and self-quarantines, our lives will be changed. But and people believe that. And for instance, articles like this actually influence times like this. These dips may have happened coming down. These dips may have happened because of articles like this. How the magic more often the cases appeared. I'm going to go back to the models though here to just because. So we have modeling basics here, and so what I've been talking about so far is that you're looking at data to make predictions. Okay, so you're trying to figure out how I can see into the future. How can I go into the future and see what's going to happen based upon the data that I have now, the historical data that I have right now? How can I extract meaning from that data to see about what's going to happen here? So that's really what this is all about. All of data analytics, I would say, is about extracting meaning from data to make, I would say, to make decisions, to take some action, to make some type of prediction. And if you make a decision, you're trying to predict what kinds of problems may come up, and so therefore you make a decision to to avoid some kind of hardship. And so I would say that all analytics really is a kind of a modeling system here, just to make predictions or to help you to avoid some kind of catastrophe that would happen. So today what we're talking about is one of the more popular ways of making models to make decisions, and that's going to be called linear regression. Linear models are actually very, very popular. In fact, there's no end to them. Whenever you go online and you read articles, especially like, for instance, where you're talking about like the stock market, or you're reading about, in my area, bioinformatics, or you're reading about medical informatics, or you're looking at something where they're trying to predict something. Chances are they're going to be using this word regression, or they'll use linear regression according to our linear regression models, or according to our multivariate regression models, which is right down here. But the again, it's this word regression. And so regression is really kind of using these numbers to illustrate a trend, trying to figure out what's going to happen. So that's really what we're talking about today. Like, what is regression? Before I get to regression, I'll talk about some other kinds of popular machine or models that you see, like machine-based models. We have for instance, another model we have is are called support vector machines. Now these all do the same thing. The approach that they have is different, but they all do the same thing, and that is that they take historical data and they try and figure out where that historical data is going to go. So here we have this is what's called a supervised learning model. Supervised means that you have to have an idea about what to expect, and you have to guide the model. So in the support vector machine, you're feeding it data, but you yourself, the user of this program, you have a notion of what this model should be predicting. You have an idea about what's going to be coming out of this model. However, if you have unsupervised, that means that the model can just be set to go. It can find the data and then make its own assessments. And whatever the data says, like when you wake up in the morning after having run it the night before, whatever the model says should be what's going, or it should be an accurate prediction. But supervised means you have to stay up all night with this model and kind of keep nudging it every now and then so that it doesn't kind of fly off the rails. But it's a supervised learning model with learning algorithms. And when I say learning algorithms, what that means is it's looking at the data just as we saw before. In fact, I'll go back here. Just as we saw before, it's looking at this data and saying, aha, I see that the numbers are climbing right about now. That suggests to me that because this climbing information, because it's climbing right here, maybe there's other information here too, but it suggests that since this is climbing, that the numbers will continue to climb. And so when you use a learning algorithm, it's saying I have noticed this trend of the data either escalating or de-escalating. So anyway, but it's an algorithm that analyzes the data, and it's used for the classification and regression analysis. And by classification, what that's talking about is it's finding certain types of patterns which exist in that data. So in going back to our maps here, the classification could be these points from this point here up to present day are climbing, whereas this point here, 98 days ago, down to this point here, they were declining. That means that the cases were going down. And so that is really what they mean by this classification, finding out what those trends are. So that's one thing here, support vector machines. We have generalized linear models. We're going to be touching on that today. Flexible generalization of ordinary linear regression that allows for response variables that have an error distribution other than the normal distribution. In other words, you're using models to predict data, and the data has a strange type of conformation. That means a strange distribution. One of the problems with these types of models it's like you can't just pour any old data into them and expect them to work, which is why we have so many different models. It's like, for instance, there are many different liquids available out there, but you can't just pour any old liquid into your glass because it might be cleaning fluid and it's not good for you to drink. You can only drink, water and lemonade and those kinds of things. And so while something looks like a drink, it may not be. And so while something looks like data for a model, it may not be. Then we have generalized additive models here. These are models that are used where you have some kind of a predictor, a linear predictor, and you're using like maybe our smooth functions and predictors. Again, it's a kind of it's a plotting tool where you're looking at where the data has been, and you're trying to figure out with some kind of, you have a focus on where the smooth functions are taking you. Again, it's just a plotting tool. We've actually done this in our heads. When we looked at this data here, we're actually looking at these, our eyes are following these lines, and we're figuring out in our heads where these numbers are going. These models I'm talking about here are actually just algorithms that do exactly that, that return some kind of information that kind of, they actually return a statistical measurement. Linear regression is another one here. We'll be touching on that too. It's a linear approach for modeling the relationship between a dependent variable and an independent variable. In other words, how does one thing depend on another? We do have slides that talk about that. And then we have this loss regression, another kind of regression here where you're using other types of tools because the data that you're working with may not actually work here because this doesn't accept certain types of data types or distributions. Combining much of the simplicity of linear least square regression, but building with the flexibility of nonlinear regression. So for instance, today we're talking about lines that are basically straight lines, but if you have like data that's exponential or it's going in strange curves, you wouldn't use a straight line, you'd use something like this. But anyway, forget all that for now. Let's talk about those lines in a moment here. This is actually an interesting idea here. I just chose this one at random. This is called logistic regression. Actually, it wasn't so random. I see this actually being mentioned in papers seemingly all the time. But logistic regression can be categorized by, you have categorical variables, hours studying at the bottom here on the in the plot, and then you have on the y-axis, you have the probability of passing an exam. So what you're looking at here is categorical variables, which have like one of two values. It's either 1 or it's 0. And so if I have a whole bunch of binary data like that, can I use regression to figure out how many hours I'll spend studying and how I can expect to do on exams? And it turns out that you can. So you can see on the bottom here that the points, hours spent studying, you can see how they're just kind of all scattered along the x-axis here. Each point, by the way, represents a value of x on the bottom, and each point, sorry, an x and a y. Sorry, each is x and a y, and then you can see that these points along the bottom here are hours spent, like maybe 3 hours, and you have like maybe a 0 probability of passing an exam. But if you look at the top of the graph here, you have more time spent studying, and then you have this 1 for the probability of passing an exam. What this is saying, though, is that your probability is fit between 0 and 1. So this curve is giving you kind of an idea about how to expect the amount of time that you put into studying affects the amount of time, the kinds of grades that you get. But the data, and I don't have the data to show you here, but the data is really quite binary. I think we'll just move on here. But I think that one of the best ways to show you kind of like how to use these models is simply to just to show you a model being made and being used to answer a question. So really, we have two different types of questions that I'd like to answer here. I think actually the question that we're going to be tackling first is not question 1, but I think we'll go to that later. But we'll say that, do hotter places have more crime? And do taller people make more money? These are the types of questions that you can actually answer with these models. And the reason why you can answer these questions with models is because notice how both of these questions have to be very informed about the historical data surrounding the issue. So let's look at the first question here. Do taller people make more money? Well, in order to make an answer, in order to actually answer that question with any certainty, you'd have to know traditionally what people make. What kind of money do people make? And then you'd have to know whether the people were tall or were they not tall. And so you have to have a kind of historical data to kind of find a trend. And then once you have that trend, you draw a line through the data, and then you say, aha, I found that there is a trend that as people, in fact, I'll tell you, that taller people do tend to make more money. That's just what the data says. Now, we don't know why that is. We still have to go back and figure that out. The data suggests that taller people make more. And then we have a question two, do like hotter places or do warmer places have more crime? Again, this is a question that can only be answered when you have some kind of traditional data that behind it. And so we're going to be using modeling to actually answer the question. But I have this big what if here, because when you're creating a model, what you're doing is you're taking the data that you have from some kind of tradition of some kind of historical data, stuff that's already happened, and then you're creating kind of you're creating a system of well, a line equation, I guess. I'll talk about this in a second here, but you're essentially creating a giant line that just goes through the data, and then we can imagine that that line is indicative of whatever value of whatever values of x we put into it. So by modeling, we can ask what if questions, where we can say, for instance, going back to this question here, do taller people make more money? Well, I can say, well, based upon the idea that tall people do make more money, what if I have a friend who is 6 feet tall? Can I expect that in general he would make more money or she would make more money than somebody who is 4 feet tall? And you can answer this question by the model. But one thing I will say, and I'll stress this to you, and that is that you're just creating a model. It doesn't suggest that this is truth. It's just a model, and the model is a computational framework which just provides you with ideas about what is happening, but it doesn't mean that this is exactly what's going on. Because if you think about it, models could be dangerous. I went around with a notion to say that tall people, if you're tall, you're making a lot of money, then that is actually dangerous because I'm being severely misled. That's not always a hard and fast rule. But models, though, produce a kind of an indication of the general trend of the data that you've been using. You shouldn't say that, that your model that you found with a particular data set is how it always is with every data set. You always have to know that, for instance, different data sets, different models, different people, different interests in music. That's how I used to think of it. Anyway, before we get into that, let me just talk about these functions. So a model is really kind of a line that exists. It's like a line of data, if you will, that exists, that if you plot it, you'll get a kind of a picture that looks like this. And so this is a temperature going up, crime going up. That's what our x and y axes are. They do say that when you're in countries where the temperatures get warmer, crime does tend to go up. But again, this isn't always the case. This is just what the models predict based upon the data. The data that we have may have biases in itself to influence our thinking and to turn us down the wrong avenue. Anyway, but you have a line here. This is really what I'm talking about here. The lines, these lines represent functions. That means that my x and my y values here make a whole bunch of points. And when I plot those points together, each of those Cartesian points, and I stand back and look at it, I get a line. And so we have these functions which exist here. So these are all the points that come together to create these lines. And these represent kind of like the natural trends of my x's and y's. In this case, you have a straight line on the absolute left. In the middle, we have a kind of a curvy line, and then we have another curvy line on the right. So these lines are really suggesting what the data looks like if you were to plot it. Now, these are like mathematical lines here. Use a mathematical equation, and you plot your data, you'll get this. But in reality, your data actually falls into like clumps of information that surround these lines. So, for instance, here on the left side, these are each point here represents somewhere where I have a value of temperature and a value for crime. I have a whole bunch of points, and I just put them on my plot like this, and I can see, for instance, that I can actually draw a straight line through them. And this suggests a positive correlation between temperature and crime. So you can see that actually what we're doing is we're drawing a line through this data. And so that's really where these lines are coming from here. But this line, in fact, I'll just cut to the chase here. This line that we're drawing through this data actually can be mathematically pronounced. That means we can actually figure out what that line is that we're drawing. So it's a perfect line that still follows the data through. Now, in general, the reason why we care about a line is because when we're putting together, when we actually do plot our data, um, sometimes the data is spread out; it's all over the place, and so it's really hard to see exactly what's going on. Is the line going up? Is it curvy? Is it straight? If I look at the middle plot here, I could potentially argue that it's a straight line and not a curvy line. Although we know from this data set here, which is exactly the same data set, they just cherry pick their data, I think, with more vigor. It's the same data set, but here you could it's not so recognizable that the line is a curvy line. In fact, even here on the absolute left-hand side for that straight line, you could argue that it's not exactly straight. And so it's difficult. This is what happens in real life when you're working with data. And so what we have is we have a series of models, like the algorithms I just talked about earlier, like the least, that's the squares, of uh, like the generalized linear models and linear regression, those kinds of things from back here. What they're doing is they're looking at these points and they're figuring out where that line should be. Now, the funny thing about this is that it's there's a certain randomness involved in creating these models, and so if you were to run this same thing like hundreds of times, you'll find that your lab or your line is going to show up in slightly different areas. But in general, it's the same line. So we're using a model here to try and predict where points are going to fall. I have this information here. I know where the points. I know where these points. But if I have more data and I start pouring it into this plot, could I predict that this new data is going to fit into the same cloud that the other data was in? Or, for instance, if I have data that goes above n or x is equal to 2, if it goes up to x is equal to 3, 4, 5, and 6, and 7, could I predict that that data is going to land along a line? And so that's what this model business is all about here. We have our data set, which is that stuff on the left. We have an algorithm, and then we have a model, and the model allows us to ask questions that start with, what if my x were equal to blah, blah, blah? And then I'd be able to see what would happen to y. In other words, I'd be able to see where the point would fall if I have a new x and a new y. But I remember, I remember when I first saw these models, I thought, oh my gosh, if you have the model, why bother even collecting data? I mean, it makes sense. Why would I need to collect data if I have the model? Well, the thing is, though, that you're using this model to actually, you're using the data to inform the model, using the data to inform the model. If you don't have the data, then you cannot create a model. And so you have that. So actually, the data collection is always going to be important. And it's naive to think that, oh, because we have a model, there's no reason to collect data anymore, because we might find that, for instance, different experiments, different data, different model. But before I get any further along in that, I need to talk about, for instance, what model we're working with, and we're working with what's called linear regression, where we are taking a cloud of points and just a giant cloud, and we're figuring out where a line is going to go to skewer that cloud, and that line is called our model. That means that we're expecting every single point to follow that line in some way. So we have this new vocabulary here. We have independent variables and dependent variables now to worry about. So the independent variables of an experiment are, I have a slide here someplace. Here we go. The independent variables of an experiment tend to be variables whose variation is not dependent on something else. So for instance, in this plot here, how study time affects grades. And in fact, I do have a link that you can look at right now while I'm talking about this, which is actually kind of good because here we are. This is a Plotly thing. You can actually click on things. It's exactly the same thing. I did add some graphics over this plot so that you can actually see it on your slides, but it's the same stuff. But here we have, for instance, the independent variables are the numbers of hours studied. Doesn't depend on anything. But the test grade is, you could say, is in function of the number of hours studied. That means that the more time you put into this thing, the better your test grade. It doesn't matter. It doesn't mean that the better the test grade, the more time you put into it. It's not that kind of relationship. This is saying that the number of time or the amount of time that you put into it is independent of anything else. And so your independent variables tend to follow along, here, but they tend to follow along on your x-axis, whereas your dependent variables, those variables which depend on some input, in other words, your y is really equal to y is equal to a kind of a function of x. And so your y is going to be your dependent. And so in this case here, we have these points where I wish I could see everything, but I just can't see everything where I am. But you have, for instance, well, I guess you have at x when this person studied for 1 hour, they got a 61, I guess, from whatever class this came from, and so that's the data point. When this person studied for 2 hours, they got a 77. When this person studied for 3 hours, they got a 79 and 80, which isn't bad here. I went right down. There we are. Here we are. So if you click this, I don't know if you can see where I am right now, but if you click at the top here, there's like this equals, and then this one that just has one arrow. If you click that, then you can actually see the points themselves. When this person studied for 3 hours, they got 75, and then when they studied for 3 hours again, they got 80. So it's not always perfect here, but what this model has done is it says, okay, well, here are the points that we have, and so how can I like draw a line that goes through each of these points? And when I say draw a line that goes through, what I'm saying is that between the line and the point, I am minimizing, and the line is kind of like being kind of like it's being fitted so that it goes through these the center of this cloud of points as best it can. And so that's what we call the trend line. And so this trend line, I'm not sure I like that expression, trend line. It's also what you'd call your model. So that means that, I don't know if you can see where I am right now. Okay, so where I am right now is I am at 3.5. X equals 3.5. There's no data. No one ever took a test where they had studied 3.5 or 3.5 hours. There's no data on that. But this is predicting that if somebody had taken the test or someone had studied for 3.5 hours, then they would get about an 83%. They would expect to get an 83% on their test. It's just a line. It doesn't mean that that's exactly what the truth is, but this line is saying that if the trend holds true, all these other points, then, for instance, if someone studies for 4.5 hours, then I should expect them to get a 91% on this, whatever it is. Now, this is incredibly biased and incredibly inaccurate because we have no idea what kind of test this is. Is this the same for all students, just one student? We don't know. And so that is why, for instance, there's still much research that has to be done with models, because while this may be true for one student, you cannot take the model from one student and apply it to other students. And any sharing of models doesn't usually bode very well. So what you tend to do, though, is you have a whole bunch of points from the whole class. In fact, I'll just go back here. On the left-hand side here, this data, you have a whole bunch of points from many different people, and you try and get a more kind of generalized model, whereas this model here may pertain only to one student. So it's hard to say. But you do get this idea, though, that, for instance, anywhere on the line is exactly the truth. But you can see, though, that even these points themselves, like this one here, in fact, I don't see any points that actually fell on the line. So this line is what they call an expected line, or in this case, they call it the trend line. I call this the expected line, which means that ideally, with this data, the points would be found very, very close, if not on top of this line, but it doesn't mean that that's where they always fall. So that is why the model has errors. And that is why the weatherman or weatherwoman, when they're pronouncing the weather every day, they can be wrong. Today there's going to be a massive storm, but actually the weather is nice and sunny. How did they go wrong? Well, it's because their model was predicting, by the data that they had, they were predicting that their points were going to be gathered where the rain would be found, but actually, instead, as randomness would have it, it wasn't. Anyway, so models have some problems here. Remember, it's just a line that's being forced into a place or a space, if you will, where there's a bunch of data. But mathematically, what's going on is this: you have all these points, and you have to figure out kind of an average line, if you will, and then this can't point. There's a little sigma sub I here. In fact, in your equation, y is equal to beta naught plus beta 1 x1 plus this little sigma I. What you're trying to do is you're trying to minimize that sigma value for each point and have the line, you're trying to minimize that line for each of these points here, but not have the line move too much so that it maximizes the sigma or the sigma point for anybody else. We don't have to worry about the mathematics for this whole thing here. We have software that does all this for us, but I do think it's important to give you an idea about what to expect. This line, if you remember from like maybe your algebra course, is really a y equals mx plus b type of line, where your m is your slope, like whether the line is like up and down or whether it's going straight across. You have a slope of 0, for instance, it's just a straight line that goes horizontally. If you have a positive slope, it means the line is inclining, and a negative slope means the line is declining. But that's what your slope is. This is your line equation. Y is equal to mx plus b, and in this case, b is your beta, and that's like your intercept. You can see at the bottom left, the intercept is beta naught, and that means that's like how far above the y equals 0 you are when you're at x equals. Where does the line actually cross the x? This is another picture here of really making a model where you have a whole bunch of points, and again you're putting these points onto a screen and you're trying to find out where does a line go. So actually, all this math aside, and there's a bunch of stuff that goes into this thing here, but if you think about this in terms of throw your point on the plot and figure out where a good line would go to represent those points, and then remove the points and just work with the line, that's how you make a model. It's much, much more simple if you think about it that way. If you look at the mathematics in these kinds of graphics, it becomes a little bit more complicated. I wish that, like when I first read about models, I wish they had just said, throw the points up there, figure out where the line goes, and then remove the points and then work with the line. They don't just say that, which is just really annoying. They go right into the math, and then you're immediately confused. So I'm going to avoid that. We have something else that we should talk about here, which is kind of interesting. We have the residual sum of squares, which is kind of an interesting statistic that comes out of these models here. But I'm mentioning this now. We haven't actually talked about some of the other statistics that come out of working with these models, but I'm mentioning this thing now because this is a statistic of actually how well do these or how close are these other points falling from the line that you've drawn out. So if you look at the upper plot here, you'll see that the scale on the y-axis is between 0 and 6, whereas below the scale is between 0 and 6,000. This suggests that the plot that's above, these points are actually falling much, much more closely to your line, or your prediction line, than they are if you're looking at the bottom plot. So that means that the distances are greater in the bottom plot. And that means the points are falling further away from the line than they are if they're in the top plot. That kind of makes sense, that everything's kind of more shrunk together in the top plot than in the bottom plot. But one thing I'd like to look at, though, is this value of RSS, the residual sum of the squares, which is a measurement of how well do those points fall in terms of where that line is. In other words, can you somehow get that line to be more snug? Is there a better place for it to go? Can you get better? Can those points in general be found closer to that line? And after the mathematics has happened, you've created your model and R has given you all these output data streams. You'll find this number here called the RSS, and smaller RSS numbers, in this case, the top plot has 6.4, where everything's very, very snug. The bottom plot has 6.444, where everything is actually quite, it's not so snug. Everything's kind of like spread out. And so what you're saying is that the better models, where the points are actually kind of adhere better, or they're closer to the actual model line, is where the RSS values are smaller. And I've written this down here, where I've written that the model, or the small RSS value, indicates a tighter fit. Think of this in terms of wearing shoes. You wouldn't play basketball with shoes that don't fit you, because then you'd just trip all over the place. I mean, you wouldn't wear, like, I don't know, your older brother's, huge shoes over your feet, if you're playing basketball, because then you might just trip over your own feet, and that would be bad. So you tend to want to wear shoes when you're playing sports, which actually kind of lace up and kind of hold your feet snugly so that you have the best grip as you're on the court when you're running around. And so that's kind of the way that this data or this RSS works here, is that you want a tighter fit or a smaller number to indicate better models in general. In general, sometimes there may be applications where that isn't true, but I'm going to say in general. This is just another residual. This is a conversation about residuals. A lot of when you're working with papers, for instance, where they talk about regression, they might mention the word residuals. Residual is it's the distance between the observed values and the estimated values. So I guess here we are, the observed values and the estimated values. The estimated values, that's the line. That's where everything is fitting here. But the observed values, that's what my actual data is saying. And so I'm saying how well or how snug, what kind of fit do I have with my data? Chances are you won't really be using the residuals much, but they will be there. And I mean, if you're checking to see that your model is actually a good model, you'll be checking your RSS, and then you might check this residual scores to see how snug everything is. But once you've decided that your model is as good as it's going to get, then you can ignore all this stuff and then move into the other statistics, which we'll talk about in a moment. But really what it's doing though is these residuals, that's your sum of the squares, the residuals, that's what R is. What you're doing though is you're using those residuals to figure out how snug that line goes. So anyway, let's talk about some questions that we can actually answer ourselves using models. I don't want to, we have about 20 minutes here. I'm going to get this going here. But we're going to ask this question, and we have some data. But we're going to ask a question that says, is crime influenced by yearly temperature? You might think, how can I even begin to answer that question? Well, don't worry, because we have a data set here that we can use to actually figure out how that, we have some historical data, and what we're going to do is we're going to look at that history, and we're going to create a model, and then we're going to ask some what if questions. What if the data were such and such, or what if the question, what if the crime or the temperature was this? Would we expect our temperature to change? That's our first question, and then probably not today, but maybe next, I guess a week from today, because there's no class on Tuesday. But well, the next big question we'll do is what's the impact of earning power on and personal right? How do they influence each other? So come with me if you will. I'm going to go boot up my RStudio. We have some code that we're going to be looking at. Let me just go ahead and get my studio working. Here we are. This is my studio. In fact, this is all the stuff we had left over from last time. It's crazy as that. I'm going to close all this down here, and I'm going to start up a new, whoops, I'm going to open up a new script. Can't really see what I'm working on now, but it's here. I can assure you. I'm going to save my script. Got to find a place to save it so that it doesn't get lost. Here, I'll call this focus, and I'll give it today's date, October 2020, and that should do it. Focus. I call it focus because it's kind of like I'm trying to describe the it's like it's a focus on the code. Okay, so go back to the slides if you will, and let's check out what we need to do. So the first thing we're going to do is we're going to, you don't have to run this since we just open this up, but I'm going to copy everything anyway. What this code is going to do is it's going to give us, oh, you know what, I have to format this stuff. So I need to remove this here. I have a library I need to load. These are all kind of, these are some comments here. I think what I need to do is I need to, let's go back to I'm going back to the slides here and just seeing what my notes are, or what my code is supposed to do. So my first thing is an RM list, library, and then I have a comment, and then I have C's to compile. Okay, I think that's good to go. So come back with me to my thing. There you are. I'm going to go ahead and run this. Now, I just ran the whole thing. In your actual, you can't see what I'm doing, but actually in your sandbox, you should have it actually in your sandbox somewhere. Is it? Now class docs, labs. If it isn't there, I have to put it in. It's in your, here we go. It's in your week 9 sandbox, and then you have, for instance, a file called crime. Crime. So go to your sandbox, week 9, your week 9 sandbox here, you'll find crime. And so now this is creating, what does this say here? Data C, what is this? Let me do this again. Here. Where's that? Where are you? I got this crime. This should be a CSV file, and it should just open up here. I don't know why it wasn't working before. File must be a character string. Not coming up. This is extraordinary. It, this worked last night. Choose for read CSV. Oh, you know what? You know what? I have a mistake here. I think I have to have data.c. Yeah. Oh, I know what it is. I know what it is. I just kind of... Your notes actually say this. Sorry. It just says C is equal to file.choose, then crime is equal to this. And so if I just go ahead and run this thing, let me just show you again. This is what happens when I misformat my data. Let me just go this. So anyway, I'm loading my crime file here. There we go. Now, if I look at my crime file here, the crime data, you always want to go through and look at the crime you have by state. So this is American data. You have an abbreviation of that state. Maybe that's redundant. State and abbreviation could be redundant. But you have the low is going to be the temperature. This is actually kind of a creepy statistic. The murder rate. And then we have this TC 2009. The TC 2009 is a weighted value where they're using it's a metric of the amount of crime for that particular temperature. Now I'm not exactly sure how they came up with that metric, but it's probably a number which is combined using like murder, theft, and other types of crimes, which I don't have to mention. But other kinds of crimes are probably all brought in together, and this is where this statistic actually comes from. So that number is actually some measurement of crime. And then we over there, we have the low, the measurement of the temperature. So now what I'm going to do is I'm going to go back to my slides and see what else I can do to feel really bad about my society. So we've done the view here, so we can see the crime. This is an important thing here. This kind of defines that we're working with a data frame. I'll go ahead and put that back in here. There we go. Data frame, running it. Good to go. Yeah, so we have this deappreciated, which means it could still work, but it's just not. They want to phase it out. That's okay. So anyway, what I'm suggesting is that you spend some time actually going through and making sure that your data is actually you understand what your data is doing here. So I've already done that for you. So here we have the yearly low temperature, we have the murder rate, and then we have what's called the training data. And this TC, the T must stand for training. 2009, this must be some kind of data that came from crime-related data from 2009. So we're going to do some exploratory plots here. And so the exploratory plots, remember, are just kind of creating a picture of what the data looks like now. Okay. I'm going to go back here. Come with me if you will. And then we're going to just plot this up here. And when I run this, we've seen this ggplot before. The format is the same. We're using points. This is different here. This alpha is equal to 1/4. The alpha is kind of the transparency or the opaqueness of the points. You can change that if you want and add some more stuff. Add bigger lines or smaller lines. As you change your alpha, it changes how clear how well you can see through the points. And then we have our smooth line, which is what we've seen before. The smooth line is the trend of the data. Now remember, we'd use our smooth line to kind of to see what the data is doing. But when we only concentrate on the smooth line, then we have no notion of the outliers. That's sometimes a problem, especially if those outliers are the ones that inform. Now, I'm going to show you another line, which is actually quite interesting. This is a line that is your proper linear model using least squares. So this is a line which is not necessarily going to follow the data like the previous plot, but rather this is a straight line which is a predictive plot. Now, one thing I will tell you is that when you see this line, this shadow that you see around the line, that is your confidence. That means how confident are you that, in fact, I'll get right here. How confident are you that that the data actually falls close to that line? Well, you can see that where the data in the middle between minus 40 and minus 20, or maybe actually minus 50 and minus 20 in there, the data does kind of hang close to the line. And so you could say that, for instance, you would respect the predictions of data points along that line in that interval, minus 50 to minus maybe, I don't know, maybe minus 25 in there. And you can see that you should be able to you should be able to trust those results because the shadow is close to the line. However, where we have x equals is greater than 0, we only have basically one data point on the far right. And so that shadow is actually quite wide to say, I'm really not sure where the point would fall if you had more points. They'd fall in here somewhere, but I can't say exactly where that would be. Whereas around x equals minus 40, it's saying that if you had more points, then those points would be found inside that shaded region because the model has proven itself to work. So you have these, you have this, you have to, there are trade-offs. The model doesn't always give you perfect data everywhere, but sometimes it gives you some good data in certain parts of your plot, other parts are not. So now we're going to build a more thorough model here. And this model will look like this, where we have mod is equal to the linear model. In fact, that LM is your linear model. And then we have this PC 2009, that's our statistic of prime. And we're going to regress that by low, which is the amount of temperature. And then we have to talk about what the data is. This is your actual code that you'd use in R. So this is your linear model syntax. Your low, by the way, is your independent variable. That means, you can't control the weather, it just it does its own thing. But you could argue that you can control the crime. That's something that we're arguing is dependent upon the weather. That's the whole premise of our test. So this is actually kind of interesting thing. We'll put the model in a second here. But your when you have this tilde that separates things here, it's kind of like you're saying that this is your y is equal to the a plus b part. So we're building a line equation from this data. This is just going to figure out what the x value should be and what the b value should be. So that's where this is all coming from here. Our dependent variable is dependent on the independent variable for some value of x and some value of b. And that's really what we're going to be predicting here. So before I actually run that model, we'll get to there's actually code in here in a moment. But your model is going to look like this, where it's really just a line equation. And that's this other way of looking at it. Your dependent is going to be here in blue, and your independents are going to be yeah, okay, well let's go to the model. Okay, let's do this model then. If I can just go ahead and select this whole thing here. Let's see, I go back here, come with me if you will, to the R Studio. I'm going to drop my model in here. And when I run this, nothing crazy happens. But something has happened, in that my model now is being saved to this mod. In fact, if I type in summary, you can actually see that, summary. There we go. You can see that something actually did happen. And what happened here was that this is the output of your model. So let me just take you through this. We'll actually spend more time going through this, but this is the code that you typed in. So if you printed out this whole output, then you have your model code. I mean, that's like how your code has how your model has been created. You have your residuals. Remember that the smaller residual, the smaller the RSS, the better the snugness, the better how the points fall to where the line is. In other words, it's like the accuracy, if you will. So we have information there. We have the min, max. We've seen this before. The first the 1Q here and the 3Q is your quartiles. You have your median, it's your second quartile. But you can get an idea about where these points are falling by these things. You can see that in the first quartile between 1 and 3, 50% of your data is stored between minus 647 and positive 533. And here's your max value, and here's your min value. So you get an idea that this data is actually quite spread out, as we see from our plot. That's the plot that we have that we see right now on the right-hand side is still the plot from this data. But really what we're looking at, though, is we have some information that's like down here to tell us, like, first of all, how good is this plot we have here. Now, each residual standard error, this is your RSS, on 46 degrees of freedom. Well, if we have a number of different plots where we're working with like slight variations of our data, we would want to reach for the numbers or the plots or the models for which this value is the smallest, because that would suggest that the points are falling closer to our line. And so we have some other things to look at here. I don't want to get ahead of myself. Get back to the slides and see what we're looking at here. Oh yes, really what we're looking at, though, is are these values here are my coefficients. And my coefficients are these values here. The intercept, this is if a line expression is y is equal to mx plus b, this is your b, and this is your x. Y is equal to mx plus b. That's this piece over here. This is your slope. I believe that is. And so you can go back over here and we can check this out. And so we can see that your coefficients, 4256, that's your intercept, and your low is 21. Well, how can I actually make any sense out of this whole thing here? Well, if you can just kind of, if I can get 2 slides at one slide here, my equation for my line is y is equal to alpha plus beta times x, or y is equal to ax b. This, it's the same characters for everything here, but just remember that the b in this case, or the beta, is your, that's your slope. And so over here, this value that we get, 21.64, or 21.65, I guess if you round it up, that value actually represents your slope. And so we have created a line which looks like, well, you can kind of get an idea. This is why I'm actually using it, but a line that looks like this, where the alpha is 4256 and the beta is 21.64 times x plus epsilon. And so that is this, if you look at this inside this square here, that is our actual our model that we're creating here. So y is then equal to 4256.86 plus 21.6 times x. In this case, I'm just substituting the value of minus 10 because I'm asking a question, what if x is equal to minus 10? And then I get my y value, which is 40.86. And so this value right here is a point that I would put on my plot, which comes from my prediction. So I'm really just creating a prediction. I'm predicting, saying, well, if x is equal to minus 10, then I predict that according to my model here, where I've substituted these values in, my y will be about 40.86. And so that's saying that I can now kind of create the idea, or I can create data in some ways from my model, which I have to now check to see that it actually does fall where the real data fell. But this model has been informed by the historical data that I've already looked at. And so really, just going back for a second, this page right here, these coefficients that's the hard part to actually calculate. But R does this in seemingly no time at all. And so now you have the ability to create a linear model where you can grab these coefficients, put them into your line equation, and then substitute any value you want for x, and then see what happens to y. Before I go any further, let me go back for a second here. I don't mean to make anyone feel dizzy. Here. Now, let me just show you something. And many people don't get this, but you do. And that is that notice how your data has actually fallen between the actual training data I'm talking about. The training data is falling between minus 80 and say 10. Minus 80 and 10. My training data came from minus 80 and 10. This gives me in some way, whether the model works or not, but it gives me in some way the authority to speak about a model between minus 80 and 10. But if someone says, what happens when x is equal to 400 billion, or some ridiculous number which is clearly off my plot, then I'll say, I mean, my model will come up with a number. It will predict something, but whether that number uh, has any trust in it is entirely something else. And so what I'm saying is that when you're just like kind of asking your what if questions, this value of minus 10, actually, if you go back to your thing here, minus 10 was actually in our plot that we originally plotted here. You can see that happened. That minus 10 is actually firmly on this in this collection of plot. So that means that we can actually ask this question minus 10, but anything above 10, x equals 10, and anything less than minus 80 is, I would say, strictly forbidden here. You get a result, of course, but the value that you calculate will mean nothing. And that's actually a very important thing to notice or to say, because I've read papers where people have trained a model with a very small group of data, and then they extrapolated the outputs of y on enormous quantities of data. They're saying, here's my values. I use the values between of x equals 0 and x equals 5. That was where all my data had come from to actually train my model. And then saying, what happens when x is equal to 200? Clearly off the map. And anything you come up with is not going to be. The last thing I talk about before we actually break here is this function, which is actually quite important. This is a function that you might want to use in your own work. In fact, I did use this. But this function, though, is how to use your model. So, for instance, I've already run my model here, and this has my coefficients in there. And so I'm going to create a function, and of course, it doesn't look. Of course, it's all out of its formatting here. But what I'm going to do is I'm going to create this value here called tell me why, and that's my function here. And what it's going to do is I'm going to be able just to substitute values into this function, and it's going to tell me what happens when my value of x to that. It creates a model that I can use to make my predictions. Just give me a moment here to find out where everything's supposed to go, and I believe that. So now we're going to ask ourselves, what if x is equal to minus 10? And so I get this. And so this is my model here. Hopefully it works. Using the coefficients that I found from my model that I created, my linear model from up here, where actually I'm looking at x here. I'm putting these coefficients into this into my function. And what happens now is that the function then creates a calculation based upon my line equation. Y is equal to mx plus b, or y is equal to f of x equals mx plus b. Well, here we go. I have my intercept, I have my slope, and I'm taking my slope as the mod coefficients 2, so that's this piece right here. And I'm going to be multiplying my slope by the x value, which is coming here, which is really my y, that's right, y is equal to mx plus b. That's my line equation. So what I'm doing here is my m in this case is going to be this value here, my slope. My mod efficiency 1, that's my b over here, and my x is what the user types in themselves, which is the value right here. So you can see that really I'm just saying calculate these values all together, and so this is my y equals b, and then of course there's an output sign that prints up whatever y was calculated to be. And so actually this is kind of a fun little thing here. You can kind of play around with your data and say, okay, well, what happens if y is equal to minus 10? If y is equal to minus 10, I get this 40-40, which we saw here, for instance, going back to my slides. That's where this value came from here, 40-40-86. Right, so we got that. But now, what if, I know that 1 minute over, let me just show you something that's absolutely insane. Let's just say, tell me why. let's say I have like 1,000. What's going to happen then? Well, if I run that, I get this value here. Now, that value is mathematically correct, but whether it has anything to do with my data, I mean, is this consistent with my, that's the thing. Because for instance, imagine for a moment that you're looking at data like this, maybe for instance, when the values are within a certain threshold or a window of X, then it's consistent. But otherwise, when values of X get bigger, then it's no longer consistent and your model breaks down. And so that's something that you really have to watch out for. Many of the papers that I read are using models which have broken down and they're still predicting. Models only good for certain values of X, and then after that value of X, it's down. And they're still using it to make these giantesque predictions, which are just, for instance, here, this is useless. Anyway, I'm going to go ahead and stop this here. When we come back on, actually not Tuesday next because class is going to be canceled, but when we come back on Thursday, we'll finish this and we'll get into some other modeling work too, or have some other questions I'd like to ask, and then create models. And so we will continue this then.